Today, our topic is rotational kinetic energy. So, what do you already know about energy? Probably a lot. You know that energy is conserved. The energy in the universe always stays the same. It is never created and it is never destroyed. But you probably also know that energy comes in different forms. We have potential energy like gravitational energy and spring potential energy, chemical potential energy, and we have active energy or kinetic energy. You also probably remember that work is equal to the change in energy. If I do work on a system, I take some of my energy and I give it to that system. So the system gains energy and I lose energy. You probably also remember that we represent energy in a number of different ways to help us understand what's changing in a system. Sometimes we use bar charts like the one here, sometimes we use pie charts, and sometimes we use equations. Let's consider an example. This simulation gives us a ramp. I'm going to start by adding a frictionless cube to the top and watching it slide down. You're probably pretty familiar with the energy changes in this situation. Let's consider 3 points along the ramp. At the top of the ramp, block has all gravitational energy, let's say 4 blocks. Midway down the ramp, only 2 blocks are gravitational and the remaining 2 are kinetic. And by the time it gets to the bottom of the ramp, all 4 blocks of energy are kinetic. How does rotation change the situation? Let's take a look at our simulation again. I'm going to add a hoop to the top of the ramp in addition to our frictionless block. Watch how they compare as they go down the ramp. Notice that the hoop takes longer to get to the bottom. That means that at every point along the ramp, the hoop is traveling more slowly than the block was. What does this mean for the energy of the hoop? Well, let's assume at the top of the ramp, it had 4 blocks of gravitational energy, just like we assumed for the block. When it gets to the middle, it has 2 blocks of gravitational energy, but it's not moving as fast, and so it doesn't have the full 2 blocks of kinetic energy. That means that something's missing. And when it gets to the bottom, the difference is even more pronounced. Even more energy is missing. It turns out that when an object is rotating, some of its energy is in the kinetic rotational energy. We call this rotational kinetic energy K subscript rotation, or K-rot for short. If we add the rotational energy of our hoop at each point, our bar charts now look like this. We still have a total of 4 units of gravitational energy in the first graph, and with the addition of rotational kinetic energy, our bars add up to 4 in the second and third graphs as well. But what is rotational energy? If kinetic energy was 1/2 mv squared, rotational energy has an equivalent equation. Instead of K, we will use K-rot. It will still have a 1/2, but for rotational systems, instead of mass, we end up using the rotational inertia, or inertia of the object that's rotating. And instead of the linear velocity, we will talk about the angular velocity, omega. So the equation for rotational kinetic energy is 1/2 I omega squared. The units for both kinetic energy and rotational energy are still joules. Just like linear systems, energy is conserved in rotational systems. By this, we mean that if there is no work done on a system, its energy remains constant. The difference is we have simply added a new form of energy. Work is the means by which energy is added to a system. In linear motion, the work is equal to the force multiplied by the distance that an object moves. Remember that in these cases, the force must be parallel or anti-parallel to the distance of motion. You can, for example, add energy to a rubber band by stretching it. In the rotational case, the work done is equal to the torque multiplied by the angle of rotation. For example, if you are spinning a basketball, you increase its rotational energy by applying a torque as the ball spins. Let's look at some examples. In terms of energy, what do you see happening here? Well, the man throwing the Frisbee exerts force over a distance. That does work, which means the energy of the Frisbee increases. As the Frisbee flies, you can see that it is moving and rotating. Therefore, it has kinetic and rotational kinetic energy. Let's break that down. As the man throws the Frisbee, he's applying a force to the center of mass throughout the distance of the throw. The work he is doing is equal to the force multiplied by the distance the Frisbee travels while he is throwing it. That translates into kinetic energy, which means the center of mass is moving. Notice that the force he applies is applied to the edge of the Frisbee. That means that it has a torque. As the man throws the Frisbee, he is exerting a torque in order to rotate it. The rotational work done is equal to that torque multiplied by the angle through which the Frisbee rotates while it's in his hands. This work gives the Frisbee rotational kinetic energy. Let's consider how the equations might apply in some examples. What kind of energy do you see here? As the dancer spins, her center of mass is not moving. Therefore, she has just rotational kinetic energy. If we were to write an equation for energy, we would simply write that energy equals 1/2 I omega squared. What about for the bowling ball here? Notice that as the bowling ball moves, it's spinning and the axis or center of mass is also moving. That means that as it goes, the bowling ball has both rotational kinetic energy and linear kinetic energy. An equation for its energy would look like this: 1/2 mv squared plus 1/2 I omega squared. And in terms of energy, what do we see happening here? Well, the bubble wrap is exerting a force on the dog. It's exerting a force at a distance from the axis of rotation, which means that it's also exerting a torque. And the work done by pulling the bubble wrap is becoming rotational kinetic energy. Work is equal to the change in energy. Therefore, the torque multiplied by the angle through which the dog spins is equal to 1/2 I omega, or the rotational kinetic energy of the dog. Let's consider one more example with equations. Here we have a mass connected to a heavy pulley by a string. If you release the mass, it will fall, pulling the pulley along with it. Think about the energy changes in this system. At the beginning, when the mass is at the top, it has gravitational potential energy. By the time it reaches the bottom, the mass is moving, meaning it has kinetic energy, and the pulley is rotating, meaning it has rotational kinetic energy. If we consider the equations, on the left-hand side, we have mgh for gravitational energy. On the right-hand side, we have 1/2 mv squared plus 1/2 I omega squared. The conservation of energy tells us that these two equations should be equal to each other. Since the pulley is rotating at the same rate as the mass is falling, we can use the bridge equation, which relates the linear velocity of the mass to the angular velocity of the pulley. Remember, this equation is V equals R omega. Plugging R omega in for V gives us this equation. It looks kind of messy, but if you examine it carefully, if we knew the mass and the rotational inertia of the pulley, we could easily solve for omega, the angular velocity, or we could solve for v, the linear velocity of the block. As we move through the world, objects move both translationally and rotationally. We now have the physics to describe the energy in both cases. I hope this was helpful. Happy physicsing.